In this video, we will study an actuator in Flux 3D. The actuator contains a mobile part, a magnetic circuit which is fixed, and a coil around the central part. The force applied to the mobile part depends on the position and the current will be applied. The 3D geometry definition is done in the modular context, which is a dedicated geometry building context. The simulation in Flux is done using the following steps: geometry construction, which is done in the modular context, mesh generation, physical properties definition, solving the problem, and post-processing the results. Let's start with the first step, geometry and mesh creation. We start in the supervisor. We choose a working directory and create a new Flux 3D project. Flux is now opened. First, we will create 2D geometry in the 2D geometry creation context called the sketcher. We will extrude it later. We create a new sketch defined on the YZ plane. The sketcher context is opened and we create two rectangles. The coordinates of the points are modified to create the proper dimensions. With the 2D geometry creation finished, we can close the sketcher and extrude the 2D geometry. We open the extrusion box, choose sketch_1, and the following face to extrude them. We extrude along the x-axis and the XYZ1 coordinate system with a length of 15 and an offset of -15 divided by 2. The preview is correct, so we validate the extrusion. For the next step, we will work on the coordinate system named coordsys_zx_plane. We create a cylinder with the data entered. We create a second cylinder which contains the first one. We use the symmetry tool to create the symmetric cylinders. To create this, we choose the two cylinders and ZX_plane as the symmetry reference plane. The symmetric cylinders are created. We then create a union between the magnetic circuit rectangular part and the two external cylinders that we want to keep. In order to delete the central cylinders, we select the magnetic circuit master object and subtract the two internal cylinders. The magnetic circuit is complete. We create another cylinder for the mobile part with the data entered. And complete the mobile part with another cylinder. To see a preview, we decrease the opacity and validate the dialog. Finally, we make the union between the two previous cylinders. With the geometry complete, we now create a geometric parameter to pilot the mobile part movement. A translation is used to take into account the parameter we create. First, we choose the XYZ1 coordinate system. We then choose the object to translate and choose the parameter in the Y field. To complete the geometry, we create a fillet on the lines and radius shown. The geometry definition is finished, so we can close the 3D modeler context. Now, we create the infinite box, which defines the boundary conditions. We execute the complete infinite box algorithm in order to create the missing faces and volumes. The infinite box can be hidden for the moment. Now, we are ready to mesh the geometry. For that, we execute the mesh domain command. In order to have precise results, we generate second-order elements. Now, we need to create the physical definition of the actuator. The first action is to define the physical application to study. Here, the magnetostatic application is chosen. We will study the static comportment for different mobile part positions in the current source value. Then, we import a material from the Material Database Manager. Flux is now connecting to the Material Database Manager. We sort the materials by family to easily find the material to import. We are looking for a carbon steel soft material. We take the first one and we drag and drop it into the window on the right, which represents Flux. We close the Material Manager and the connection is automatically stopped. In Flux, we find the imported material. The next step is to create the current physical parameter, which will be controlled by the solving scenario. Then, we create a coil conductor component referencing the previous current parameter. And finally, we create a non-meshed coil to define the coil's geometry in physics. It is a circular coil with a rectangular section defined in the coord_sys_zx_plane coordinate system with the data shown. For the electrical data, we select the previous coil conductor in a number of turns. The coil is now visible. Now, we create the physical volume regions which will be associated to the geometry volumes. First, we create the air region. Then, we create the support region, which is a magnetic, non-conducting region defined with the imported material. Finally, we create the mobile region with the same properties. The regions are then assigned to the volumes. With the regions assigned, the physical definition is now complete. Now we can define the solving scenario and solve the problem. In the solving scenario, we will pilot the position and the current. For the geometric parameter, we want to solve for the values 1, 3, and 5. For the current, we want to solve for the values 3, 6, and 9 ampere. Now, we can run the solver to solve the project. After a few minutes, the project is solved. With the solver complete, we can post-process the results. Post-processing can be done in a graphical manner. We display the default ISO values, which correspond to the magnetic flux density in all the non-vacuum regions. We can also display the arrows of the magnetic field on the magnetic circuit. Finally, we can create a 3D curve of the force applied on the mobile part depending on the position and the current.